Okay, we'll make a start. Welcome to the Thursday afternoon lecture. So we've got a double one today, so it'll be the usual. Have a lecture till, what is it now, 4:10. So around about 5 o'clock, 5 to 5, have a short break, and then start up again from 5 to 6, going through exercise sheet 2. I've had a couple of queries regarding the exercise sheets. So when are they coming out? When will we go through them? So between now and Easter, which is 4 more weeks till the Easter break, after this week, I'll release them on the Tuesday of the odd weeks. So next Tuesday I'll release sheet 3, and the week after, which will be week 7, I'll release sheet 4, and then we'll go through examples on the Thursday, the second lecture of the even weeks. Okay, one other comment. I didn't hit the wide button on the camera till about 10 minutes into the last lecture, but fortunately it did capture all the first 2 written boards. So if you are looking back at that and you want to look at what was written, it's all there. Just hit the pause button in about 15 minutes. Okay, so where we got to? So we just proved Theorem 4.1 and Corollary 4.1. So this says that P divides AB, then P divides A, or P divides B. It might be that P divides both of them. But it's not an AND statement. And we'll use this later on as a strong definition of a prime number. Our definition at the moment is based on a number dividing P. So if D divides the prime P, P equals D times E for some integer E, whereas this is based on what numbers does P divide, which is a subtle distinction but important. We also proved Corollary 4.1, and that says that if a prime P divides A1, A2 up to A little n, then it must divide one of those. So let's say it divides AI for some 1 less than or equal to I less than or equal to n. So that's where we got to. We're going to round up chapter 4 in this first lecture. So we now have enough machinery that we can prove the uniqueness of integers factorising into prime numbers, up to rearrangement of the factors. Okay, so every integer, a, strictly greater than 1. Remember, we don't include 1 as a prime, because if we did, then 1 would have many prime factorizations, 1 times 1, 1 times 1 times 1. It wouldn't be unique. So this is why 1 is sort of above being prime. So I'm not going to concern myself with whether primes are repeated yet or not. Because that's much simpler. Once we know the factorization is unique, not worrying about repeats, we can then simply collect the repeats together. Okay, so proof. Well, our statement says all integers greater than 1. Well, what's the smallest integer greater than 1? And it's 2. So so it's true in that case, because 2 is a prime number, an even prime, and there's only one way of writing it, because it's a single prime number. So the theorem is true when A equals 2. Okay, so we're going to do an induction again. Sorry about that, looking in the mic. Remember last time on the corollary 4.1, we inducted on the index. This time we're going to induct on the number itself. So 2 less than or equal to A, less than or equal to n minus 1. You can, if you prefer an n, you can always do your induction that you assume true up to n and then look at n plus 1. It's just a matter of convention, really, and notation. And we consider n equals P1, P2 up to Pn. So we're going to, as usual, assume the converse So we're going to assume that P's and Q's are all prime numbers. So we better state that it's for all 1 less than or equal to y less than or equal to n, 1 less than or equal to j less than or equal to m. Okay, so I put corollary 4.1 up for ease of reference. So let's take P1 and P1 must divide the right-hand side because Q1 to Qm over P1 is an integer, it's a product of integers. And because P1 is a prime number, it must divide one of the Q's, call it Qk. Okay, so k will be one of the m possible values. And so Qk is P1 times E for some integer E. Okay, we now use the fact that Qk is a prime number. So Qk is P1E for some E. So P1 divides Qk. So this is our current definition of a prime number. If the prime divides, if a number divides a prime, taking Qk as a prime, then of the two factors, the only possibilities are 1 or the prime itself. But P1 by definition is greater than or equal to 2, which implies P1 equals Qk. So we can now cancel P1 with Qk. And that will give us P2 to Pn is the product of the Q's with Qk missing. Okay, so we're going to get something like this. That P2, P3 times together up to Pn must equal Q1 times Q2 up to Qk minus 1. Omit the Qk, then Qk plus 1 up to Qm. Key point is that because we've cancelled a factor that's 2 or greater, our number n is now diminished to less than n. So now we're nearly home and dry. So by our inductive hypothesis, we have to have that the P2 to Pn are the remaining Qj in some order. And so we can also deduce from that, as they pair up, that n equals m. Okay, so factorisation of integers into prime numbers up to the ordering of the prime factors is unique. I've got to write down the corollary. So what we call the canonical form it hasn't got a number. It should have a number. It should be corollary 4.2. Okay, so we can group repeated prime numbers, or prime factors. Let's call them factors. We can also order the primes. So let's say increasing in size. So I'll give two ways of writing this. So let's say every integer, we use little n or a, we're using a's here. A in the natural numbers. As the unique representation A equals P1 to the alpha 1, P2 to the alpha 2, PR to the alpha R, with P1 strictly less than P2, strictly less than PR. And each alpha I, now this is one way of doing it. You can say greater than or equal to 1, or greater than 0, as it says in the notes. But sometimes, and we'll find this in proving the third proof of infinitely many primes, it's also useful to write them as the infinite list of primes and allow alpha to be 0. So shall I use A's? I use alphas. Okay, stay with the alphas. 2 to the alpha 2, 3 to the alpha 3, 5 to the alpha 5, 7 to the alpha 7, each alpha j greater than or equal to 0. Alpha p, sorry, alpha p. So, let's try and turn this around a bit. This is a sort of unique representation. It only involves the prime factors appearing in the number, and it assumes that each of the exponents is at least 1. But this, you write down the infinite list of prime numbers and allow the exponent to be 0 or greater, and you can also write each number that way. Okay, so we'll have a remark. So we now apply theorem 4.1 as the strong definition. Of a prime number. So you've probably come across in algebra and analysis the idea of irreducible polynomials. Anyone? Yes. So you think of a polynomial as being irreducible if you can't factor it in any way. You can't take a linear factor x minus n or a quadratic or a... So the general idea is you can't split it in a non-trivial way. And so in terms of our prime definitions, our first definition is looking at it from that angle. What numbers divide a prime number? What happens if a number d divides a prime? But when you get into more abstract algebra to do with ideals, prime ideals, it's this, the stronger definition about what happens when a number is divisible by a prime that becomes important. But both concepts are very useful. And so the important thing that we must do now is show that they're equivalent. So the things we're very lucky with, especially in pure maths, is that we're blessed with absoluteness. Whereas when Newton was working out the force of gravity, 9.81 meters per second, it depended whether he was stood on a fairly tall hill or in some deep ravine. And so there was never an absolute answer, and there never is really to these sort of physical attributes. But the important thing is that we're consistent. So the most famous example of inconsistency is, so you've probably all heard of it, the Russell's paradox. Have you all heard of that? Bertrand Russell? Okay. Shaking of heads generally. So there was a big push towards the end of the 1800s to have a consistency in mathematics, axioms, set theory, something that you couldn't trip yourself up on. And they're still used today, the Franco-Zumulo axioms around about 1901. And they worked very hard to make them totally consistent. And then Bertrand Russell, he did it through set theory, came up with a paradox that no one could fix. And these axioms are very useful. They worked on things like parity, evenness, oddness, algebra, standardized techniques. So sort of a slightly less abstract way of describing it is you've got a group of barbers and they only shave the people that don't shave themselves. Okay? So then imagine that you've got a barber in that group that doesn't shave himself. So he's going to be shaved by the other barbers because he satisfies the criteria in the group, but they only shave the people that don't shave themselves. But he's one of the barbers in the group. So he must shave himself because he only shaves the people that don't shave themselves. And so you get this paradox. You can look it up on Wikipedia very easily for the set theory analogy, but no one could fix it. It upset all the people working on it at the time, but it's still incredibly famous. Okay, so whilst wiping the board and digressing, so we're now going to apply theorem 4.1 as a strong definition with two ofs. I was thinking about wiping the board at that point. Of a prime number. So So definition. So we say, as usual, an integer p strictly greater than 1 is a prime number if whenever P divides AB then either P divides A or P divides B, and it might be that P divides both A and B because it's an OR statement. Okay, so we want to prove consistency. So the weak definition implies the strong definition and similarly the other way around. The strong implies the weak. Okay, so how do we do these? Well, we take the first statement. You'll find that the first statement of the weak definition is D divides P, so P is DE. So we start with that, if we're going to do weak implies strong. Which one am I doing? Strong implies weak, sorry. Let's do that one first. So we assume P divides AB implies P divides A or P divides B, and we consider D divides P implies P is DE. So we want to be able to deduce that either D is P and E is 1, or E is P and D is 1. Okay, so P is DE. So I'm just going to carry on with the implies, which implies P divides DE, which implies P divides D, or P divides E by strong definition. Okay, so we started with D divides P. So D divides P and P divides D implies P equals D and E equals 1. So that was easy. So case II, if E divides P, sorry, have I got that the right way around? P divides D, that's right. P divides E, that's what I want. So P divides E, but P is greater than or equal to 2, and P equals DE implies D and E are less than or equal to P. Okay, so you've got a number whose largest value is P and P divides it, so we now get P equals E and D equals 1. Okay, so just to complete this now, we need weak implies strong. Okay, so what do we do here? So we assume, so last time we assumed the strong definition, so here we assume D divides P implies P equals DE with D equals P, E equals 1, or D equals 1 and E equals P. So that's our assumption. And now we start off with the first line of the strong definition, which is if P divides AB. So we consider now if P divides AB. So we want to deduce that either P divides A or P divides B. So how do we look at this? Well, if P divides A, we've got what we want. Because it satisfies the formulae. We don't have to worry about B if P divides A. So let's consider P doesn't divide A. If P does not divide A, then set D is the highest common factor of A and P. Okay, and D can't be equal to P. Otherwise, the highest common factor of P and P would be P. And P would divide A. So D divides A and D divides P. Now we're assuming the weak definition, which implies P equals DE for some E. So by the weak definition, either D is P, E is 1, or D is 1, E is P. But we've ruled out one of those because we're in the case P doesn't divide A, which means D can't equal P. So we must have D is 1 and E is P. Okay, have I stated by the weak definition recently? So I haven't, so I'll put that down again.
Did you mean to write D equals 1?
No, I didn't. Thank you. Thank you very much. E is P. And it's the one, thank you very much, it's the one that's important because we can use Euclid's algorithm. So by Euclid, so let's write out the full chain. D equals the highest common factor of A and P, which equals 1. We've deduced that much, which is lambda A plus mu times P for some integers lambda mu. So lambda mu, one of them is usually negative, so and now we multiply through by B. So that gives me B equals lambda AB plus mu PB. Okay, so the first, we're nearly there. First statement of the strong definition says if P divides AB. That means AB equals PU for some U. So if I factorise it, I replace AB with PU, and I get lambda PU plus mu PB. So I factorise out the P, and I get P. So the lambda AB becomes, so I get a lambda U, and then I get a mu B, right hand side is divisible by P, so the left hand side is divisible by P. Well, that was what we wanted, wasn't it? But we've assumed the weak definition. We've said what happens if P divides AB. Can we deduce either P divides A or P divides B? P divides A, well, we're home and dry. Let's say P doesn't divide A. And that concludes the proof. So P divides left-hand side, it's that same argument. Okay, so I think we can have a happy face. Thank you for pointing out that E was P. It's those sort of small things you look back on your notes and you think, that makes no sense whatsoever. So we'll stop there for a short break. I'm going to wipe a couple of boards down and then grab a cup of tea, and I'll be back at 10 past. We'll carry on till 6. So, and we'll go through some of the examples on exercise sheet 2. Solutions to the sheet are there, as are chapters 3, 4, 5. So please, if you like a hard copy, please grab one. Okay, welcome back. Right, let's welcome back. Let's hopefully a bit louder. Well, it would be if it was fallen off. Right. Let's just check the cameras on what it should be again. Okay. Okay, so I was going to work through some of the questions on exercise sheet 2. I only had one inquiry, and that was over the question 7, so I'll make sure I cover that. I'm going to use mainly the extended Euclid's algorithm. So the key points to remember are that at the last step, your remainder is 0. Okay, so that means that the n-1th remainder is the whole multiple of the nth remainder. And your quotient in the last step has to be at least 2. Because the remainders are always decreasing. sorry, the other way around, Ri minus 1 is always greater than Ri. And then the final one, Rn is 0. Rn plus 1 is 0. So we've done a couple of examples in lectures. So I thought to start with the slightly more involved examples. So question 2a. Quotients produced by Euclid's algorithm are 1, 2, 3, 4, 5 in that order. Greatest common divisor was 2. So this is probably quite a good one to start off with. So we have I, Qi, Ri, Xi, Yi. And we always start with i's minus 1, and there are no Qi values for those because we're setting up what is effectively row operations. And so you get the unit matrix here. Okay, and we're told that the Qi are the same as the I. So 1, 2, 3, 4, 5. So remember, Ri, if we have A and B here, equals AXI plus B Yi. So you get this nice property that follows all the way through. Okay, so what else do we know? This is all we're told. We're told what the Qi are. We know the last remainder is 0. And does it tell us anything else? The highest common factor or greatest common divisor is 2. So 2 has to go in there. So we've actually got enough information to work backwards now. So you get 5 times 2 gives you 10, and then plus the 0. So maybe I should write this here. 10 is 5 times 2. And then we do the same. 4 times 10 plus 2 gives this remainder, the second one. Okay, so this is R3. So we're dealing strictly with the relationship with the remainders. So 4 times 10 plus 2 is 42. So that's R2. So we can just repeat this. 3 42s plus 10, well, it's 126 plus 10, 136. So that's R1. So now we can get B, 2 times 136 plus 42. So that's 272 plus 42, 274, 314. First three digits of pi. So that's B. So we know what B is, and then with A, 1 times 314 plus 136. So that's going to be 4, 4, and 10, 450. So what does the question actually ask us? What were the two numbers? So we found the two numbers. Now, we can fill the rest of it in if we wanted to. So just to remind ourselves, if we were doing it the usual fashion, and sorry, it should be the unit matrix, not something completely different. So the usual fashion is we'd start with just those top two rows. And we'd say, how many times does B go into A? Well, it goes once. What's the remainder? And then with the once, we'd go that row minus 1 times that row. So 1 times 0 is 1. 0 times 1 is minus 1. And then we carry on. So how many 136s in 314, two of them. So 2 times that from that leaves 42. So now we have 0 minus 2 times 1, which is minus 2. 1 minus 2 times minus 1, which is 1 plus 2, which is 3. And so if we carry on in that fashion, we get 7 minus 10 minus 30, 43. 157 minus 225. And remember the last one, if you ignore the minus signs, will give you the two numbers you started, their ratio in lowest terms. So note 225 over 157 is 450 over 314 in lowest terms. Okay, so just thinking about it from a different angle. Start off with the quotients. What does B ask? It says, why can't the final quotient ever be 1? And the answer, I think we've stated up there, is no, because you always find that that is an exact multiple of the remainder above. So the final quotient, if it was 1, would mean that was 2 and that was 2. So that's no. Okay, the next one's quite an interesting example. Question 3 involves the Fibonacci numbers. So it says the smallest pair of positive integers for which Euclid's algorithm takes 5 steps is 13 and 8. Find the smallest pairs for which the algorithm takes 4 steps, 6 steps. So I'll just start from scratch on this one. So I'll ignore the 13 and 8. So smallest numbers, A and B, in Euclid's algorithm with a maximum number of steps. Let's put a new pen, that one's starting to fade. Well, it must have, if you think about the numbers increasing. So this column is always increasing, the remainder column. And it's the quotients that are really playing the part in how quickly it increases. Multiplied by 5, multiplied by 4, multiplied by 3. Now we know the last one can't be 1, we've just discussed that. So the smallest that one can be is 2, and then the smallest all the other ones can be is 1. So Ri minus 1 equals Ri plus Ri plus 1 apart from last step when smallest quotient is 2, not 1. Okay, so let's draw our table over here. Actually, I don't need to go across there, do I? Because let's say we have the I column, the QI column, and the RI column. And we can generate this because we're saying, well, the QI are all 1 apart from the last one is 2. So what should we go down to? Minus 1, 0, 1, 2, 3, 4, 5, 6. Let's go down to 6 because I've run out of board. And those two don't have a QI. And then we're saying they're all going to be 1. And I'm stopping at 6. The last one has to be 2. So let's say that one is 0. And then I get, using Ri minus 1 is Ri plus Ri plus 1. I don't have to worry about the Q's. So the smallest number I can start with is R5 is 1. And then 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. And if I carry on like this, 3 plus 5 is 8. 5 plus 8 is 13. So you probably will recognise those as the Fibonacci sequence. Have you solved the Fibonacci sequence explicitly in any of your courses? Good. Okay, so you know all about this. Super. So I don't have to derive the solution. So Fibonacci, son of Bernacchi, as he was, that works. Thank you. Okay, so this gives 0, 1, 2, 3, 5, 8. Yep. Right. It's missing. Right, I hadn't noticed this before. Right, yeah, the last step messes up the, of course it does, because you don't get that. So Fibonacci sequence, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3. But at the last step, you get a whole multiple, so 0 plus 1 does not equal 2. Thank you, yeah. So with a 1 missing. So after 5 steps, you do indeed get 13 and 8. And after 4 steps, I can chop it off here. And I get 8 and 5. And then after n steps, so I'll be careful to read it off this to make sure I'm not one out. So let's put the F numbers in. So this is F0, F1, this would be F2, F3, F. I got that right? F0, F1, F2, F4, F5, F6, F7. 8. So if that's F8, 7, 6, 5, 4. Yeah, that's right. 2, 3, 4. So let's put the Fn numbers in. So you get F7. So 4 is 8 and 5, which is F6. So F6, F5, 13 and 8, F7, F6. So AB is Fm plus 2, Fn plus 1. Smallest integers that take n steps. Okay, yeah, do you study properties of the Fibonacci sequence? Divisibility properties at all? No? But you've had the closed form expression, have you? Right. So a fact if m divides n, Fm divides Fn. So it's actually not that many sequences. They're called divisibility sequences. So here, if I carried on up, F8 is 21, F4 is 3, 4 divides 8, 3 divides 21. And one other one just to finish on this. So 5 is F5. So I'll just say similarly. And a final comment while we're on this. So if you have a general recurrence relation, and they didn't used to teach this, but I'd be interested to know if you've seen it before. So say you have Gn plus R equals Gn plus R minus 1 plus Gn plus R minus 2 plus Gn, say, then your recurrence polynomial is, you literally put the subscripts up. If I take it all over the other side, let's put, so I put Gn. And divide by, what shall I say, x to the n plus 1, so I've got a constant term. X to the n minus 1. The n plus 1 divided by x to the n, that goes, no, x to the n would give, here's x to the n, that would give you x to the r minus x to the r minus 1, and sorry, these should be all minuses. Minus x minus 1 equals 0, and the roots phi 1, phi 2 up to phi r form a basis for the closed form expression of the sequence. So let's say g of t equals, so these are coefficients, a1 phi 1 to the t plus a2 phi 2 to the t plus ar phi r to the t. So I find it one of the most amazing things. If you ever come across a recurrence relation, you can write down the recurrence polynomial and the roots, solve the first few terms for the coefficients, so the Fibonacci sequence is called Binet's formulae. It's of that form and you solve for A and B. But recurrence relations in general, if you have, so this is a 3-term recurrence relation, you will get a degree 2 recurrence polynomial, the roots of which then form a basis for generating all the sequences. Okay, question 4. So solve, this is quite a quick one, 11x minus 7y equals 2. And it's saying any solutions. Let's try and get through this one quite quickly so I can get to question 7. So I had someone ask me about the negative because it's minus 7y not plus. And so all you do is you carry on as normal, carry on as if it's positive, and then adjust for the minus sign at the end. So my unit matrix, and I'm going to start off with 11 and 7, and then my first 7 goes into 11 once, and that leaves 4. And subtracting the second row from the first row, I get 4, 1, minus 1. And then 4 goes into 7 once, remainder 3. 0 minus 1 is minus 1. 1 minus minus 1 is 2. And carrying on similarly, if I get there, 3 into 4 goes 1, remainder 1. And I get a 2 and a minus 3. And then finally, you get a 3, 0, 7, and minus 1. I should get a minus there, shouldn't I? Minus 1, minus 3 2's, minus 7. And so the highest common factor is last non-zero remainder. So 1 is 11 times 2. And now we've got to adjust for the sign. So that's a minus 3, it's going to go to a plus 3. So it's going to go minus 7 times plus 3. Asks us to solve 11x minus 7y is 2. So we get 2 is 11 times 4 minus 7 times plus 6. General solution is little x is the capital X, which is 4. And we're going to add on, no, I'm going to subtract. So the coefficient of the y is minus 7. So I'm going to subtract multiples of that, which mean it goes plus. So x is 4 plus 7t, and y is 6 plus 11t. And you get positive solutions x, y are both positive. Okay, final example. So question 7. So you're told a party of 41 persons, eat dinner at an inn. There are men, women and children. 4 sous for each man, 3 sous for each woman, and a third of a sou for each child. And the confusing thing here is having the third for the child. So what do we know? We know there are 41 people, or persons, let's use the word persons. So let's call them x plus y plus z is 41. So men, women, and z is children. And what else do we know? That the total, I got this right, yeah, 40. So the total cost is 40 sous, and we'll get 4 for each man, 3 for each woman, and a third for each child. So 4x plus 3y, is it 3? Yep. Plus a third z is 40. So it's slightly obfuscated. So what can you tell straight away? If this is an integer solution, that must be a multiple of 3. So 3 divides z as 40 is a whole number. So let's set or say z equals 3u. So we've got 2 equations. So we get 4x plus 3y plus u is 40, and x plus y. So what did we do with the first one? Well, z is 3u, so we get 3u equals 41. So this is really only the tricky bit with solving this. So if I call these 1 and 2, and then I eliminate u. So if I have 3 times equation 1 to get to 3u minus equation 2, that gives us, so it's going to be 11x plus 8y equals 79. So I'm getting a bit low on time. So this is now in the form of a standard Cattle problem, so you know how to solve it. You could solve this now. Okay, so I won't go through the table. You'll be able to do that. So I'll do a wiggle. So we find, so that means after some work. So capital X, Y equals 237 and minus 316 is a solution. Okay. general solution, you would get 237 for the x. I'd subtract multiples of 8. So let's just 237 minus 8t, and little y is minus 316 plus 11t. So I'll just, last 2 minutes, finish off on this little bit. So we solve for x, y greater than or equal to 0. And you get only one value, you get t is 29. And that in turn gives x equals 5, y equals 3. I'll just finish this off. So x is 5 and y is 3. That makes z quite big, doesn't it? In x plus y plus z equals 41. So 5 plus 3 is 8, from 41 is 33, implies z equals 33. So probably a school outing. So this is one of Martin Huxley's, who was a professor of number theory here for many years. So his take on this, which is what colour clothes do you think they were wearing? Probably a school outing, 3 nuns, 5 priests, probably in black. So that last bit is not the sort of question you will be asked in exams. I'll just say school outing. So that's 6 o'clock. So thank you very much for staying for the late shift. Thank you for pointing out that I hadn't noticed before. The extra 1. You stop. Okay, so today, Thursday. Have a good rest of the week, and I'll see you next Tuesday.